To the second session on the limaçon, or what Americans would call the limacon, and also known as Pascal's snail. So today we'll look at how we can derive the polar equations of the limaçon, and then move forward to see how we could derive the Cartesian equation from the polar expression. And we'll proceed from there, looking at the different kinds of the limacon. We'll look at what is known as the tricentrics, and then we'll move forward to how a limacon would become a cardioid and then a dimpled one. So we'll look at those three scenarios and the equations. And then in the preceding videos, we'll look at area of the outer loop, of the inner loop, the length or the arc length of the limaçon, of the inner, the outer arc, and so on. So very interesting things to come ahead. If you have not subscribed to our channel, we do encourage you to subscribe to our channel. If you haven't liked, please just spare a second and like our video. If you feel inclined to share, please feel free to share. Thank you. So let's go ahead and begin on this. Previous video, we said that this limaçon or a limacon would be derived if we had a circle of a specific radius, let's say for example radius a, and then we would divide the circumference into n number of points equally spaced, and then we would get a line that we would draw on point, but first of all we have to create a pivot. Point A would act as a pivot, and then we would draw a line, let's say of a given length k on both sides of the point. So and then this line is going to be rotated, and as it's rotated with A as the pivot, the locus traced by the edge of this line here with the line fixed with the pivot fixed at A, that locus is a limaçon or a limacon. So that's where we stopped from. So we're going to use this construct or this definition to go ahead and derive the polar equations of a limaçon. A line of length 2k, in other words k on both sides of the points on which it's centered and rotated from a fixed pivot A. So in other words, this line is k on both sides. So, and this is the center here, and then rotated from this point. Okay. So let's take this snapshot of what happens when we're trying to draw a limaçon, right? So we have the pivot A here, and then we do have the center point of the limaçon here, right? And so it's going to be k, and also this side k. So this is the middle point, and P is going to be on the limaçon, and also P prime is going to be on the limaçon. And so the diameter being 2a, and since this is our pivot, it's going to be the center point from which now we have angle theta that now defines the position of the radius, the extent of the radius. So what happens now is that the base is going to be equal to, and the base is going to be from here to here, is going to be 2a cosine theta. Why is that the case? There's always a rule that the angle subtended at the center of a circle, which is obviously a straight line, this is 180 degrees, is twice the angle subtended at the circumference. So this is going to be equal to 90 degrees. And so you have a right angle triangle, and this is being the hypotenuse. This is the hypotenuse. So the base of our right angle triangle here is going to be equal to 2a cosine theta. And what that means is that our radius now is from this point to point P is, let's ignore P prime for now, is 2a cosine theta plus k. That is the radius. Okay, so let's proceed. So since we now have our radius being 2a cosine theta plus k, that means is that x is 2a cosine theta plus k times cosine theta, and then y is going to be equal to 2a cosine theta plus k. So these are what we will call our polar equations. So let's move a step further now and look at how we may be able to derive the Cartesian equation from what we have right now. We're now going to show how we can quickly derive the Cartesian equation from the set of polar expressions that we derived previously, knowing that the radius is 2a cosine theta plus k, a being the radius of the base circle, and then x therefore becomes 2a cosine theta plus k times cosine theta. Then obviously y is also 2a cosine theta plus k times sine theta. From this expression, it's easy to see that rho cosine theta is just another form of what we have here. Rho cosine theta is x, and then if we multiply rho onto both the left and right hand side of this expression, we have rho squared being equal to 2a rho cosine theta plus rho k. So from here, it's also easy to see that if we square rho, it's the same as x squared plus y squared. So if we plug the x squared plus y squared in place of rho squared, then we're also going to get x squared plus y squared equals to 2a. In place of rho cosine theta here, we have x, so that will be equal to 2x plus rho k. And then now if we take this to the left hand side and square it, we have x squared plus y squared minus 2ax all squared equals to rho squared times k squared. Plug in here x squared plus y squared, we get the final equation of x squared plus y squared equals to 2ax all squared equals to x squared plus y squared times k squared. And that is the Cartesian equation of our Limaçon. So let's move forward and see three separate forms of Limaçon, with k being the parameter that we can sweep. So let's see two scenarios, actually three, where we vary the length k of that line that sweeps around, and see how that changes the shape of the Limaçon we get. Okay, so we do have our base circle as shown here, and then we divide the base circle at the circumference into the multiple points that we had mentioned, and we begin by putting in a line there, and obviously a pivot at k. And let's begin with k being equal to 2a. Let's begin with a. and so that it's A, radius on both sides. So the total length K on both sides is A, on the other side is A. And so when we draw the limaçon, we see that the limaçon has this inner loop, and the specific name for this limaçon is a trisectrix. We're going to show why it's called a trisectrix in a minute, but let's then vary the length of the line, move forward so that it's 2A, it's twice the radius on both sides. And then when we sweep, we see that the loop disappears. At 2A, that is the threshold, and that is actually a cardioid. If you don't know what a cardioid is, we have previous videos that you can go back and see. So when K equals to 2A, it's a cardioid. When K is equals to 3A, it becomes something else. What we call here is it's a dimpled limaçon or limacon. And it varies at various lengths greater than, when K is greater than 2A is when you get this dimpled limacon or limaçon. So those are three instances: trisectrix, cardioid, and the dimpled limaçon. We're going to see why the trisectrix name is actually used in our next couple of videos. So we just went into Desmos to try and see how we may be able to plot the Cartesian equation. We have three separate Cartesian equations with K as the parameter for which we've changed the values, and we've set A, the radius of the circle, the base circle, to be 1. As you can see in the first scenario, K is equals to A, and that is a red plot. As you can see, that is the trisectrix shown here. And then we've now changed the K to 2A. The green plot is a cardioid, so the loop just disappeared. And now when we change K to 3A, thrice the radius of the base circle, now we just have a cardioid, a limacon that is dimpled. So interesting way you can choose to use Cartesian equations, or you could choose to use the parametric polar equations and still be able to come to the same plotting. So until next time, bye bye, be blessed, and if you haven't subscribed, we do encourage you to subscribe to our channel. And yeah, bye bye.